My name is Niels Buch from the University of Copenhagen. I will be presenting our work on a new and novel material and technique called LaSir. In this presentation, we'll go through why this research is important, what LaSir is, the technique that accompanies the material, what our methods have been to develop LaSir. We will show some designed applications, and lastly, the work that is to come. In fabrication, the process of structural design and circuitry design is isolated. Prototyping uses digital fabrication to fabricate structures of the device. The design of the structure can give room for shell or tubes to hold the wires, but not the traces themselves. The designer will have to use precious time to assemble the wires afterwards. This design decreases the iterative process of prototyping and increases the manual work required by the designer. SIGCHI has a wealth of research into this field. One of the widespread techniques is to use fused filament fabrication. 3D printers with conductive thermoplastics can create structural traces, but 3D printers are slow compared to the speed of the laser cutter. Research on the laser cutter is plentiful, but often the focus will be mechanical only or require heavily modified machines or materials. LaSir, a multi-layered laser-cuttable material to co-fabricate circuitry or structural components. By combining the structural design and the circuitry design, we can decrease the manual labor and increase the positive effect of repeatability and shareability of digital fabrication. LaSir suggests a laser-cuttable 3-layered material, combining the conductive core with the insulating layers and harnessing the precision and speed of the laser cutter. As a composite material, it allows us to have a material that can both be conductive and non-conductive by cutting to different depths of the composite to change the conductive structure of the material. The upper and lower layer of the material is an insulating layer and is the structural material. These layers provide a mechanical support to the conductive layer and also serve to protect it from environmental factors. By cutting through these layers, we can create shapes and joints to create interactive objects. By only cutting through the top layer, we can create access points for the middle conductive layer. At its core lies a conductive layer. Acting as the material's electric backbone, this layer facilitates the transmission of signals or power through the material. Using a laser cutter, we can cut traces or completely isolate zones of conductivity into the material and choose our electric design. To use this technique, we suggest 4 different cuts. The cut type depends on the speed of the laser cutter and the focus. This allows us to use single SVG file to encompass the different settings. The first cut is the through cut. Cutting through all the layers allows us to control the general shape of the design. The second cut is the trace cut. By increasing the speed of the laser cutter, the trace cut cuts through the top layer and the middle layer. With this, we can create small traces of our signal or power to run. It also allows us to cut through zones of conductivity. The trace cut, however, weakens the structure of the design. Where structure is important, we suggest a third cut, trace cut with heel. This is a supplementary cut. The cut defocuses the laser by running through the laser around the first cut. We melt the top layer of the insulator, creating a bridge of the top layer to strengthen the structure. The last suggested cut is the revealing cut. By speeding up the laser, we can cut through only the top layer, allowing us to reveal the conductive contact points. The cuts allow us to make joint connections. By using a revealing cut, we can make a connection from the side of the through cut to the revealing contact point. This connection can be pushed together, and by using a wedge, have a stable connection between the 2 sheets. The trace cut also allows us to make a designated area for conductivity. This allows us to make capacitive button or sliders. Using different cuts, we can also add off-the-shelf connectors to our design. This does require manual labor to install, but allows us to use pre-made material from the hardware store. The design suggests that it allows for conductivity by using conductive connectors. Screws are a fast way to connect the different materials or to make a stable connection. Cutting a snug fit hole for the screw insert and a bigger revealing cut allows us easy access to heat set the insert. Magnetic connectors can be made by making a revealing cut to reveal the connection between the magnet and the conductive layer. Healing around the magnet allows us for a bond between the magnet and the structure. It is possible to have a connection by press-fitting hardware into the cut. We show this by using a ball bearing. To create LaCir, we have been exploring a lot of different materials and thicknesses, using different speeds of the laser cut to find out the most efficient way to cut through the material tested. Going too fast leaves the material without proper bond, or not being able to cut through the conductive material at all. To make a trace cut, we tested multiple cuts and found out that 2 close cuts are effective to cutting the connection. We have also worked on the technical evaluation. We've created a repeatable joint block to test resistance without joint, with 1 joint, or with 2 joints. Resistance of the material was consistent, but we found out that the small changes of the joint changed the resistance. Our joinery is dry-fitted with only a wedge keeping them together. To test LaCir, we created a PCB to showcase flyover traces, a Wheel of Fortune game, and a rocket lamp. In the future, we'd like to scale up the design. The current design has been held back by the size of the connectivity layer we could buy. We'd also like to incorporate existing techniques for laser cutting literature to incorporate mechanical functionality into our design. LaCir's design phase is front-heavy. A design tool will greatly help the speed of the process. There are all the materials we'd like to test too. Testing stronger laser cutters or other subtractive fabrication machines will mitigate some of the challenges we've had. I'd like to thank you all for listening to my presentation, and I give a sincere thanks to all the wonderful people who have worked with me on this project.